All right. Well, welcome everyone to the inaugural ISC software class. This is going to be on the Git version control system. I'm sure if you've any of you have worked with software, you've touched Git in some form. But I found that they don't really teach Git that well here, if at all. So really, what I'd like to go through is more of a brief, more theoretical half of Git. Less so like type this command to do X, but more here's what it's actually doing when you do X to avoid things like merge conflicts and stuff like that I think is a little unclear unless you like dig deep into the Git documentation, which is not very enjoyable in my experience. So hopefully this should be a bit more of a easier way to engage with that half of Git. There we go. All right, so first off, why is Git? What is Git? Essentially, Git, being a version control system, is for controlling versions of your files. But more specifically, it allows for extremely granular documentation of changes, pretty much. So you can think of those as versions, but that's where the term version control system comes from. So really, Git is used for a few main purposes. The first and its original purpose with Linux, which is what it was created for, was for replication. So that is having a code base and duplicating it across the world, because of course Linux is supposed to be like a distributed development effort. They didn't want to have one place that, like at the time would be like Microsoft SUSE or whatever. But over time, it's become used, and even in Linux, it was designed for this, as a medium of collaboration. So it makes working with other people on the same code base easier. And then also just honestly as a backup form. It's pretty solid. That's one of the things I think most people would get out of using Git, is just an efficient means of backing up their code. So it's used basically everywhere. If you touch software, you're going to use Git at some point, and especially in industry, it's just downright required to do anything. So here at ISC, we of course use this for all of our software, be it on Phoenix or hopefully TinyCart, just because it enhances teamwork and collaboration so dramatically that it's almost a gimme. So, as I mentioned before, what this really covers is kind of, one, how to clone open source software and how to not so much contribute, but just work with it. In a future presentation, I'll cover like GitHub and how we use it and all of that interaction if you haven't touched that before. But basically, after this, you should be able to, like, I have a GitHub repository. I want to interact with it, say push, pull. I want to make changes to it. I want to, get changes from it and understand the basics of what's occurring when you do something like work with branches or merging, and a little more of the concepts that are simple on paper, but can have some issues if you use them, in a real large project. So first off, the very basics, but all of this matters a lot. And this is one of the things that I think aren't taught that well. And if you don't explain this, then a lot of the rest is just kind of hand waved away. So at the lowest level, Git is just a tree. That's all it is, a linked list essentially. In this linked list, each node is a commit, and in each of these commits, it contains data of what has changed since the prior commit. So that would be a diff. So basically, the actual structure you can see of Git there, of a Git repository in specific, is simply a tree of these gits pointing to, or gits of these commits pointing to the next commit or the prior commit, however it's set up. So really, under the hood, this is all it is. So when I talk about commits, it is just a singular unit in what is effectively a linked list or tree. And each of those commits, all they contain is simply what's changed since the prior commit. So everything on Git is based upon this very simple concept. In addition, this is something I didn't talk about much in the past, but I found it's useful to point out here. Branches, I refer to them kind of in a weird form here, but branches, which we'll talk more about later, are simply pointers into this tree structure. So basically, in this example, we have main and stable. Each of those are just pointers. Essentially, you have the tag main, and that points to a certain commit. There's a bit more under the hood of like how that works with like cryptography, hashing stuff, but that doesn't really matter for your side of things. What matters is just when we talk about a branch, it's all the same structure. It's just a pointer to a specific node in this tree. So it's not like it's a separate structure at all. It's just a means of referencing the main tree. So these are like the objects that we'll be touching on for the rest of this discussion. So here's a little hyper simple visualization of this, just to give an idea of what I mean by it has diffs. So on the top here, I have like my example file. Git can track literally anything, but I think text is the most clear form. In the middle is our nodes, it's our commits, and at the bottom is the diff of what is changed in each commit. So you can see with the first one there, we just start off with hello. Our pointer for our main branch is just on the base commit. You can see when we add world in the second, that we commit again. We'll see one, our pointer for main will move forward a commit, and then secondly, we'll see there's the actual information in that commit is just the world. So in the actual commit, this will also contain like which line changed. So it's on line 2, we added world. So then you can see why that matters is that if you have a change to that same line, the next commit will then be what was there and what's there now. So in this case, we removed the world and we added the smiley face. Again, the main pointer gets moved one forward. So the reason I mention this so much, and I believe I get into it a bit more in the next few slides, is that because we have these prior commits and because these commits are simply what's changed since the prior, we can super easily go and basically revert changes or reapply changes from basically between any two continuous points. So let's say in this last example we have hello and main there. Let's say we want to go back to the first. There was a git command. In this case, it's specifically like git revert ~3 head or something like that. That will go and move that main pointer from that red node all the way back to the beginning. And then because Git has what's changed in each of these commits, it can simply reverse these pluses and minuses to just change the file state to back to where it was without having to recreate the entire repository, which in the case of like a large company could be literal like gigabytes of files. So this is what makes Git so capable of tracking something like Linux, which has literally millions of commits on it, where it becomes basically an algorithm problem at this point. And it's this kind of like flexible structure that allows it to do things like branches, which we'll touch on later. So actually, this is exactly what I was just saying. So in this case, the reason I mentioned those branch pointers earlier is because specifically it allows you to move through that tree easily because they're just pointers. You just reassign the pointer, and then you can very easily and in a lightweight manner revert back to prior changes or revert to current changes, literally with one command in like a few milliseconds, which is really where the power of Git comes in and why it's taken off so much compared to its competitors in like the 90s, but they almost don't exist anymore. And I mentioned down there, this is what it means by versioning, is that each of these commits are a version of the software. Version we think of like v1.0, v2.0, but each of these are a version of the software in a way. It's you made a change, it is now a new version, is essentially how the language goes. So before I go further, do we have any questions on like this basic concept? Yes.
Is that pretty much like it allows undo and redo pretty easily in simple terms?
Yeah, exactly. Yeah. Cool. Anything else? No? Awesome. So we'll get to a lot more interesting examples, but I just want to make sure that everyone had that down. So I'm going to go out of order here compared to most guides and introduce remotes here, because I think this is another great example of why commits existing as they are really makes Git a usable tool. So remotes are essentially just a Git repository on someone else's computer. Probably the most common that you'll interact with is GitHub. But you could make your quote-unquote own GitHub by just hosting a Git server on a server somewhere. It's nothing fancy. But essentially, this is just a Git repository, which, remember, is just that chain of Git commits on someone else's computer. And because of this, if you have the same repository on two computers and you want to collaborate, you can utilize that commit structure to easily share changes between each other. So what I'm going to talk about here is basically how collaboration works in Git at like the node level. So generally the workflow, if you haven't done this is something you may have touched already, is a remote generally already exists. Like let's say it's a GitHub repository. Generally, you'll check out that repository, which I'll get to later. And then you make a change to it, you make that commit, then you do what's called pushing that commit, which is sending that commit over to the remote. And then in let's say someone else is also working with your code, so there's like 3 people in the scenario, or 2 people in the remote. That person would then pull your commit. So in Git lingo, pushing is sending data, pulling is taking data down. As well, you can fetch, which is just pulling without actually making changes to your side, and we'll get to branches later. But that's just to get the lingo down. So what does this look like in practice? So we have our local repo and our remote there. So you can notice the remote has different changes than us. And in particular, you can see it has one more commit that we don't have. So in this case, we would say in Git terms, the remote is ahead of local. Local being on our computer, remote of course being on the server. So right now, if we use git pull, Git will notice that there's one more node on their tree. It will then send only the information in that node over the network and simply append it to our tree, move the main pointer, and then that's it. Importantly, in this process, you also apply the changes that are in that commit to our files. That's how it actually changes the code on your computer. The important part of all this is, again, it's only the changes that have changed. So in a massive code base, you're not copying all of the files every time. You're just copying a few kilobytes, which is really, really where the power of this comes in. I'm not going to actually do this yet. I want to get to branches first, and then I want to have a bit of a demo of merge conflicts later. So Git's main feature when it was introduced compared to prior solutions, because you probably noticed that you can effectively use like a Google Docs edit history as a really bad Git, because that is its own version control system in a way. But really what makes Git different, and why I recommend not using Google Docs as your means of sharing code, is branches. This is really its killer feature. So I've mentioned a bit before how it's just a pointer, but really as we'll go through here, it's a really powerful feature that you can use to make things like testing different versions of code extremely simple compared to how you'd have to do it without Git or with, again, something like a Google Doc. So here's an example. So we have, what's my little story here? Oh yeah, it's a feature test between different versions of Happy Smiley and Angry Smiley. So let's say we have on our main branch, we have our Happy Smiley here. And this is on a branch that we call Smiley. Again, that's just a pointer to our commit that has this. Then let's say we want to change to our other thing we're cross-testing with, so our Angry Smiley face there. Oh, we make a new commit, name this branch nice, and then you'll see now that there are just simply 2 branches in play. Each of them are just 2 different pointers. So nothing has changed on the actual tree other than the addition of new commit, but under the hood, we've just added 2 pointers. So even though those are different branches, they're still fundamentally on the same structure. It's just 2 views over the same structure, essentially. Now, the nice thing is that if we then do what's called a git checkout, so checkout in Git terms is simply we want to change our physical files to a different branch. If we run that checkout to nice or smiley, it will basically step its way through the tree and reapply or unapply changes that are found in each of those commits, so in each of those diffs. And so it'll rebuild or kind of tear down the repository. Now, why that's useful is like this example. So let's say we're showing like a client or something. Imagine this is like a UI. We're showing them our beautiful smiley face. They're like, it's okay. We want to show them the other version. So all we have to do is just check out the other one. It'll reapply the changes, and then we're instantly at that older state. And then, of course, because it's Git, we didn't lose any of those old changes. This is, again, where it's different over something like copy-pasting into like a Google Doc or like a FTP server, because in that case, you would have lost your old changes because you've reverted. But in this case, because we can have both branches active at the same time, because it's just doing this like almost like a mutable transition between these Git nodes, we don't have any risk of losing our work here, and we can almost instantaneously swap between the 2 versions. So in practicality, this could be something like, let's say you're making a really risky change to your code base. Like you're like, oh, I think we get a massive performance boost if we change this function or whatever. And you're like just tearing up the code base trying to do it, like changing parameters everywhere. If you do that in a separate branch, none of those changes are permanent. None of those changes are damaging. And I think this is something that a lot of people new to Git don't really realize too much. It's something that people learn from experience. but really using this as like a defensive mechanism to not blow up their code base is one of the most useful uses for Git in my experience, especially with robotics, where tuning random configuration files are kind of like half of the field. So, brief mention, branches and remotes actually work together the same as commits. That is, if you have a branch that you want to send over to a remote, it will just send that information about your pointer, so that is what its tag is and what commit it's pointing at, over to the remote, and that way you can sync the two. Pretty easy, actually. The only thing to note here is that generally the kind of syntax for this is to have a almost like a URL where it's the name of your remote / the name of the branch on your remote. So if you're, for example, pushing and pulling to a specific branch, it's generally like origin or remote or something along those lines, and then just the branch. All right, I'm actually doing the demo this time. So this I set up last year. Oh, hopefully it works. Cool. This is a very silly repo. It's the United States Constitution, historically accurate. My favorite parts is if you go into pull requests and look at closed pull requests. These are each of the failed constitutional amendments in pull request form with like actual accurate authors and stuff. It's crazy. I love this repo. What's the issues? Oh, it's like an actual issue. Anyways, it's very silly. You have commits from like 1883. And I'm going to use this as an example of just messing with everything we just talked about. I've got to do it one-handed, so we'll see how easy this is. This as well should give you a good example, if you haven't messed with Git too much, of the verbiage of like git clone, git push, git pull, all that sort of stuff. So I'll copy it here, go to my trusty terminal, which will open on the wrong screen. Oh, it's so small. Hold up. Problem of not having a mic stand. There we go. All right. So let me go to my development folder. And then, of course, if you ever used Git before, you'll recognize this. So we have this. This is our Git remote. We want to put this on our local. To do that, you just do git clone and then the URL. So what we now that we know this node structure, you can recognize what this is doing is it's actually just sending all of your Git, all of those commits, and then just replaying the changes on all of them. So on the server, there's no actual files being stored. It's simply the Git tree itself, which is I think pretty interesting. Anyways, we just do that. Pretty easy. What did I say we were gonna do in the slide? Oh, that's not it. Oh, right. Yeah. Okay, so what I was gonna have us do is test out a new constitutional amendment. Which, of course, in terms of risky changes you can do to something, I think that's up there. Sorry if this is very small in person or in the recording. This is a very high-resolution TV, and Linux does not like it. So here's our amendments. In this case, let's see what branch we're on. Zoom in. I don't think that helps.
I mean, can you do it again?
Did it go in?
It did. It went in.
Oh, it's approaching.
That's better.
There we go. Significantly better. Oh, it's so laggy. This poor XPS 13 was not made for this. Oh, I was in power saving mode. That's fine. All right. Anyways, so if you're in a Git repository and you want to find what branch you're on, what commit you're on, etc., there's this beautiful command git status, and it just gives you all that information. So you can see we're on a branch called master. Generally, master or main is like your default branch. It's up to date with the origin there. So again, we're up to date with the remote. That makes sense. And then you can see there's nothing to commit, working tree clean. So this just means that you have made no changes. If you've made changes, it'll say which files and what you want to commit, if so. So in this case, let's make a new branch. To do that, you can just do git checkout. Oh, if I can spell. Tech B. Like, how many amendments do we have? Like 21? 27? Okay, it's the 28th amendment. I haven't had a history class in a hot minute. Is that valid branch name? It is. Okay, so you can see now we're on a branch called 28. If we do git status, it'll say we're on branch 28. And if we view our actual log, which is the list of git commits, we can see my favorite amendment, additional markdown formatting. We can see this is our actual commits. These are your commit IDs. These are messages, author, date, etc. Oh, there it is. There's the James Madison. I love this. I love this repo so much.
1999.
Yeah, 97 right there. A wheelchair amendment. I haven't heard of this. Anyways, history lessons. Author Congress. That's so good. By the way, you can edit any of these variables like author, date, etc. It's like if you see like Linus Torvalds in one of our repos, that's not actually the creator of Linux. You can just set your name to be whatever, and there's no way to check that unless you sign your commits with like a cryptographic thing. Anyways, let's make some changes. Let us add 0, 0, 0. They've planned ahead with all these zeros. Right, so you can see in something like VS Code, you'll see this U to symbolize a file. That just means that's U for uncommitted changes. So that's changes that are not yet reflected in the actual Git tree itself. Copy over. I think that's correct. All right, so I'll leave it to you, the people, for we are a democratic club here. What shall be the 28th Amendment of the United States of America? I will not put that in this video. I want my monetization, thank you. Someone give me something that won't get us demonetized. Can burn flags? That's already constitutional. We could make it an amendment.
Free college tuition.
Free. I like this man. All right. No more words are necessary. It's just simply free college tuition. How do you spell tuition? T-I-O-N. That period. Excellent. So now with our incredible amendment here, if we get status again, you'll see that we'll actually have like a get status to display. If I could spell it right. It's a demo, don't worry. Hey, the amount of times I've typed in :build or ROS3 is incredible. Anyways, you'll see here at the bottom, we have untracked files. This is because we've added a new file. This just means that Git isn't even looking for changes in these files. So what you do is you do git add and then the file name. You can just keep auto-completing and it'll work. So now you'll see changes to be committed. That means these are changes that the next time we commit will be saved in that commit. This way you can separate changes into different commits. Like let's say we added like 3 different files. You can choose which files to go into which commit just to organize things better and make it a lot more of like an actual trackable version log. So then let's do that. Do our little commit. You can add a little message. I don't know. Good ideas. And then we can see, of course, it is in our log here. And then we'll do something interesting with this in a second. But first, I want to talk about the mythical merging, the part of Git people don't actually understand, and really why is it not full screen? The reason I made this presentation in the first place, because I did not understand this for the longest time, and I could not figure out why things kept breaking. To the extent, at some level, nobody really understands Git. If you reach a certain level of complexity with branches, it just gets ridiculous. Like merging branches from like 3 branches removed on both sides. But in its basic form, merging is pretty simple and pretty useful because, like, cool, we have a new branch. What do we do with it? Like, you can't have main 1 through like main 55 every time you make a change. So really, all merging is taking your changes you have in a different branch and then simply messing with the pointers on the tree to make it so you can kind of think and at a high level that you're like smashing that branch into the other one. I'd like to make that a bit more clear of like what's actually going on under the hood, because it's easy to say, oh, we're merging 2 things together. It's easy to visualize that, but when you get into merge conflicts especially, it's really useful to know why that's actually occurring, because the magic breaks pretty quickly. And the key thing here is that merging isn't actually always done in the same way. This is what I didn't realize for a long time. There are, I think, 3, and each of them have their own pros and cons and can be done in certain scenarios. So the nice one is fast forward, also called a rebase. If you hear rebase, it's this. Essentially, all you do is, let's say we're merging nice into smiley. So you can see nice is ahead of smiley. You can only merge new information. You can't merge away information. That doesn't really make sense. So we want to make smiley be equal to nice. So because we have 1 commit forward, we simply, when we're on smiley, we run the command git merge nice. This is something I didn't realize. You want to be on the branch that you're merging into when you run these commands. The documentation doesn't really make that clear. And then in this case, we can see, because if we view this from the pointers and tree structure, it's just a line, right? So the only thing we have to do to make smiley reach nice is to simply just reassign the pointer, and it's done. So that's what Git calls a fast forward. It's just replaying commits till one's equal to the other. This is by far the easiest and nicest way to merge. It's really only going to happen on super small projects, though, because most of the time you'll have enough changes that things will diverge, and this really only works if you only have like 1 or 2 branches. But still, if you can keep things easy, try to make it this, especially on your own personal projects. Try to make it so you can have whatever branch you're merging into be as linear as possible. I see some people make like branches on branches on branches on branches, and then this just isn't possible because Git has to shuffle around so many pointers that things just kind of get messed up, as we'll see in the next slide. All right, here we go. This is the real one. This is the commit or the merge everyone knows. So basically, it's what it says on the slide probably says it in a more simple way. But essentially, when you have divergent state, so like basically, if you have 2 equally possible like branches, essentially, this is why it's a tree. We haven't actually seen this yet, but you can see you can point to these arrows should be in the opposite direction, which is how this makes sense. But it's not just a linked list. It's a linked list, but there can be multiple like parent nodes, essentially. And so this is basically how these branches that are completely divergent would look. The important thing here is that if you notice, it's not actually that simple to merge one into the other, because what it actually does under the hood is rewind your state to the most common base node and then replay one branch's changes onto the other. Hopefully that's clear. So like for example, in this case, we would what are we merging? We're merging nice into smiley. So we're on this node. What it would do is it would rewind our state back to here, then apply smiley, then apply nice. And this is to basically take into account all possible changes on both branches. I believe in the next slide I explain the actual issue with that. But it's important to note how it actually does that is it rewinds all those changes and then makes a new commit at the end. And that's your 3-way commit. So if you ever see a commit on a GitHub repository that's like merged in #23 PR or whatever, that's what that is. It's just basically a commit that just summarizes the changes in that merge. So the issue with this, what if both branches change the same thing? In this case, you notice, like, let's say both of these change the same line. Which one does Git work with, right? Because it's reversing and it's reapplying both. Then you get into weird things where it's like, is it just the most recent one that applied it? Maybe. I think that, that's a decent heuristic. But on a large project, at that point, what if you weren't expecting someone to have changed a file recently, and then it just overwrites your code on your other branch without realizing it? There's lots of really tricky situations like that. And so instead of trying to do a heuristic and make you potentially lose code, Git very smartly makes it your problem. So if you've ever tried to merge and got a merge conflict, this is what the merge conflict actually is. It's just simply two possible states, and Git has no idea which one it should use, so it just kind of tosses the problem your way and says handle it. So the way in which you actually work on it, I don't think I have a visualization of this. I will show us in action in a second, though. The way you actually fix this in the normal Git usage, IDEs kind of change this, is it'll add arrows, so like right arrows, left arrows, around each area that there's a conflict, and then it'll have a bunch of equal signs forming a line between each divergent state, and then you simply delete the stuff you don't want and then run another commit. That will become the three-way commit. So that is the new three-way commit. It's your changes you just added, and then that'll resolve it. Make sure you delete the arrows. The amount of repositories I've seen that still have Git merged like conflicts in them committed is insane. One of the hackathon teams that won last year or in the spring had like 3 merge conflicts in their main branch. I'm like, guys, come on, I think you won this. But the amount of people in ISC as well, like they get C++ compiler errors, and it's like, what's invalid syntax? What's this? And it's like an entire line of arrows from a merge conflict. But we'll see that quickly. Here's the challenge. Let's see if we can purposefully make a merge conflict. Oh, how did I do this last time? I have to think about this for a second. It's really easy to do these things by accident. It's really hard to do them on purpose. How would I merge conflict here? Let's make another alternative 20th Amendment. I think that's what we'd have to do. I may have to stare at the slide for a second more. This is why merge conflicts are tricky. Is they're hard to reason about for like a human.
You could roll back a commit and then branch off of it, I think.
And then merge that into main. Yeah, you're right. Yeah, you're right. Let's do that. This is why you rehearse your presentations. Get checkout master. Cool, we're on master. You can see the file deleted. And then, actually, this is a good example in general of the fact you can go back in time, and because branches are just pointers, you can create a branch off an older version. So you don't have to branch off the newest version. Like I actually had a friend who was working on a project recently who was like, all of these changes recently are bad, but I'm going to fix them later. But he had to add some other random feature that required a working version of the code. He just created a branch off the last working version of the code, and then that just works because it's just pointing to an older commit. There's nothing wrong with that, which I thought was pretty neat. Anyways, yeah, now we're on main. I think a lot of the reason that I'm overthinking this is that Git does actually, like, it's not fighting you here. It does actually want to help you. So, a lot of the weird inconsistencies, like just because you have 2 commits that change the same file, like doesn't necessarily mean it, like you can change a file, like that's valid. It's specifically when there's been changes you don't have on your branch that conflict with new changes you'd like to apply. It's probably the more efficient way to say it. So like the reason this is going to conflict is because we're going to create a new commit on main, and then this branch is not going to have seen that yet. So when we're going to merge it in, we're going to merge in changes that the person who's working on that branch wouldn't have been aware of occurring yet. So I think that may make this a little more clear since I've confused myself here. Let's do it again. All right, what's an evil 28th Amendment? What's the alternative choice? Can't do paid college because that's already like normal. Double tuition. I like thinking like a real senator. Double tuition costs. Angry smiley face.
Does the error occur then when you commit this?
No. So that's a good point. So this only occurs at the time of merging, because this is a completely valid scenario. Like, just because it's going to conflict isn't a bad thing. It's just you should be aware of what it's doing.
This is the main.
Correct.
Yeah.
Okay.
Yeah. So this is going to append to main.
If you committed this, but then went the other branch and then committed that branch, is when you would have an error.
No, it's only at the time of merging.
Merging.
And what's cool, and after we merge conflict, I may set this up, is you can merge main into a branch that branched off of main, and that's how you would actually solve this. That's keeping your branch up to speed, or up to main, or whatever. It's the lingo you'll see, because you can merge in the other way. Because merging in the other way is completely fine, unless you have also made a change, and then that's the same error, right? So it's that. You'll see on like GitHub, it'll say like one commit ahead, one commit up behind. That's when you know it's out of sync, because each branch has a commit the other one doesn't have. So merging one to the other, if they both change the same file, will always cause a conflict, and you just have to deal with that, because it's divergent state. So cool. So we'll see. Let's commit that. Actually, I have to add the file, and then we commit. Bad ideas. Cool. So now, if you'll view our log, because we're on master, we only see bad ideas. Actually, can I view this? No, I can't. Never mind. I thought I had a cool plugin for this. Anyways, cool. So now, remember how merging works. We are on main. We want to bring the other branch into us. So we're going to git merge the name of that branch that we want to merge onto ourselves. Same for rebase if you ever use a rebase.
So you want to be in the branch that is going to remain.
Exactly. Yeah. And it won't, I should mention, this won't delete your branch that you're merging from. Okay. But yeah, you want to be on the destination branch when you run the command. Simply git merge. Git merge. Was it? I forgot there's other branches here. 28th. Then we run it. Haha, it worked. So you can see, we have a merge conflict in the 28th amendment. Automatic merge fails, fix conflicts, and commit the result. Now, because we're in this very fancy text editor here, it has nice highlighting and stuff, and this is why you shouldn't work in like Notepad or whatever. But still, we're going to do this like the classic command line way, just so you've seen it, since a lot of people just abstract this away. All right. So you can see at the bottom here, we have this right arrows and 28th. This means it's the incoming change, as it says right there. This is just the branch it's coming from. And you can see up from here until these arrows, this is what we've changed from this commit that's conflicting. And then likewise for the other side. If you see head is just the current branch you're on. So head is the pointer, because you have your branches, which are pointers. Head is like a pointer. It points to the branch, which points to the node. So if you see head, just think it's the branch you're currently on. That's all it means. Head in reference to a linked list again, which is what's under the hood. And when you get the creator of Linux to write something like this, they just use CS terms in their tool. Anyways. To choose which one we want. Actually, which one do we want? Do you want the good or bad idea? More tuition or less tuition? That's the question.
More.
We got one more? More? Oh. More? Okay. We're reaching a majority.
That's one to me, so
We can meet in the middle of both, because 0 times 2 is still 0. That's very
I like this idea. That's also a very. I like you bringing this up, because I forgot you can just arbitrarily merge these two together as well, which is a good example. I like that. So let's do free college tuition, then double tuition costs. I like it. We're thinking outside the box. All right. So what I like to do is delete these. Unfortunately, we lose the cool syntax. Remember, always delete the arrows early, or else you will forget to delete the arrows. That's just kind of my rule of thumb.
What would have happened if you pressed there were buttons at the top, like accept incoming or accept?
Yeah, so those are just shortcuts in the IDE that will just, like if you said like accept incoming, it would just automatically delete all the like random text there and just accept only the bottom segment. Or accept incoming is the opposite.
The arrow would be there still.
No. The IDE would automate all that. Yeah, rarely, if ever, will you do this at this low level, but it's important to understand that this is what the IDE is still doing. But yeah, the IDE, especially for merge conflicts of like hundreds of, maybe even thousands of lines if you're in a really unlucky spot, it's nice to have a GUI that will show you each of them, and it automates it way better. Right, so double tuition costs, wait, opposite way. College tuition, then double tuition costs. This is the bipartisan compromise that we need in this country. All right. So then all we have to do is do a cool git commit. Actually, I don't know if you have to add it, so we'll check. Unmerged paths. This is why git status is nice. It just tells you what's happening. So our branch is ahead by one commit. That's because we have this commit here. Fix conflicts and run git commit. Unmerged paths. Okay, cool. So you just run git commit in this scenario. You don't have to do anything else fancy, I don't believe. Oh. Okay, you do have, never mind. You do have to actually add your changes. So a good shortcut for this, if you're working on the command line, is git commit tac A. This will accept all changes and glom them into this commit. Be careful, because if you accidentally add like 50 cached files or like node modules or something, this will just automatically add all of those to your git. So you should probably check what you're committing before you commit. But still, instead of git adding like 50 different files manually, you can just glob them all together. I believe that'll work. There we go. Oh, it wanted me to name it. So here it is. I've been saying over and over again, when you see these commits that are called like merge branch or merge PR, this is what they're coming from. Because right here, this is our commit that solves that conflict. This is our three-way merge. Git on the command line will automatically open your default text editor. Mine is nano because I don't know how to exit Vim. So you just save this file, and that'll give you the name. Cool. So now you can see, obviously our file is, as you'd expect, it's what we just committed. And then if you go to our git log here, you can see it actually doing its rewind. So this is what I was mentioning before. So you can see here it is applying each of our commits in total. So this is the last commit. See, we have our good ideas, then we have our bad ideas, and then we have our branch. So what this is actually doing is, remember, because these are from our branches. These contain the exact diff that was on that branch. So what Git is actually doing when it's doing this merge is it's applying all of our changes from one branch, applying all of the changes from the other branch, and then that third commit is resolving the conflicts between those two. And that's how it gets all the same information on one branch. That's why it has one more commit than it had before. But still, we have both of our branches, even though we've edited them, because it's the third commit that edits them. If we head back to, say, bad ideas or head back to good ideas, it would still be the state that was on our branch before we solved that merge conflict. I think you can cause a merge conflict by going back as well, but just don't do that. All right, and then, as I mentioned before, we can still go and check out the existing branch. I can spell. Just because we've merged doesn't mean that it goes away. So like none of this applies to that. It's just only the branch we merged into that changes. Cool. So just a brief summary of everything we've done. First, Git is formed by a chain of commits. Each of these commits contain only the changes made since the last commit. Git has branches, which allow you to easily have divergent changes and switch between them. You can store all of these on a remote, and everything works exactly as you'd expect, as with a local. and merge conflicts are bad, I guess. I don't know. Merge conflicts are complicated, but hopefully you understand them a bit better. I don't have a question slide, but does anyone have questions? Because I've talked a lot. No, you've asked them. Wonderful. I don't trust you. I don't know. We came to a compromise earlier. I should trust you more. All right. Well, in that case, next time I want to cover GitHub, the other half of the equation. So all of this was like the background of Git. This is ultimately like, honestly, this will get you pretty far. But this isn't really. Think of this as the computer science to the engineering of like. This is Git. What we covered today is like the science, the theory. Actually using Git in like an engineering environment is quite different because there's a lot of like hygiene, good practices, and then of course something like GitHub, tools that are yes based on Git, but are almost entirely different tools because of how much they add onto it and the workflows they promote. So next time I want to cover that, essentially just how to be a good citizen in a Git repo, and also how to do the whole contribution cycle. Last year, I found an issue in Gazebo, our raw simulator. I fixed the changed and then contributed that. So I basically go through that whole process of how do you handle contributing to other people's code, which is what I want us to follow here. It's pretty easy, but it's nice to have it clearly laid out because there's not honestly that many resources online that document it like academically. You know, it's just like a blog post or whatever. Anyways, please come to that. That's it. Goodbye. Yeah, same time.